Hello everyone. In this video, I'm going to cover the lessons for week 10 of the course. We're still in the trees unit. I'm going to be covering BTrees, decision trees, and tree visualization. There is no reading for this week because the topics in this week lessons, BTrees, decision trees, and tree visualization, are actually not in Miller and Raynham or in Zybooks. So let's take a look at L10-1 on BTrees. Learner objectives for this lesson include introducing BTrees and B+ trees, a variation of BTrees, and discuss application of these BTrees. Now, we're not going to implement B or B+ trees. We're going to introduce B and B+ trees at a high level, see some diagrams for what they look like, look at some diagrams that describe finding a data item in a B+ tree, inserting items into a B+ tree, and deleting items from a B+ tree. In this class so far, we've discussed binary trees, binary search trees, and balanced binary search trees, a variation called AVL. Now we're going to turn our attention to other implementations that are non-binary. For example, a 2-3 tree consists of nodes that are either 2 nodes or 3 nodes. A 2 node is the same as a binary search tree node. That is, the node has 2 children, and the data in the left subtree is smaller than the data at the current node, and the data in the right subtree is greater than the data at the current node. On the other hand, a 3 node contains 2 data fields, x and y, such that the first data field x is less than the second data field y. A 3 node, unlike a 2 node, has 3 children. The data in the left subtree is smaller than the data field x, the data in the middle subtree is greater than x but less than y, and the data in the right subtree is greater than the data field y. So let's take a look at an example here. So we have several 2 nodes and a few 3 nodes in this 2-3 tree. So this node, 2530, this node, 4045, this node, 6575, and this node, 105, 110, are all 3 nodes. The rest of the nodes are 2 nodes. So 50 is our root node, so everything in the left subtree is smaller than 50, and everything in the right subtree is greater than 50. So let's take a look at the left subtree. The root of the left subtree is 20. Everything less than 20 is in the left subtree, 5, 10, 15. Everything greater than 20 is in the right subtree, 25, 30, 35, 40, 45. Now let's take a look at the right subtree, 35. 35 is a 2 node, it has 2 children, but each of its children is a 3 node. So 25 and 30, 40 and 45, these nodes can have 3 children. So let's take a look at a 3 node that does have 3 children. Let's look at 65, 75. So 65 is our X data field, 75 is our Y data field. So the data in the left subtree is smaller than our X value. So everything in the left subtree is smaller than 65, which is true. 60 is smaller than 65. Everything in our middle subtree is greater than X, but less than Y. So greater than 65, but less than 75. We see 70 here. Looks good. And in our right subtree, all values will be greater than our Y data field. Y is 75, and 80 is greater than 75. The 2-3 tree is a specific case of a more general non-binary tree, the B tree. A B tree allows up to n children per node and was designated or designed for building indexes into quite large databases that are stored on disk. We're going to focus the rest of this lesson on B trees because in data analytics, you're going to be working with big data, that is large databases and data sets that are too big to fit into RAM. It is important to understand how B trees are used to manage such a large amount of data. So let's take a look at some examples of really, really large databases. So this data is from a source published in 2007, so it is already quite old, but it's still a motivating example. So look at these large data sets here, up to 6,000 terabytes, 2,800 terabytes. This one in Google we'll revisit in an example later, database with 33 trillion rows, 91 million insertions per day. That is crazy. That is huge. So this is where BTrees come in to help manage such large databases. A BTree is a tree data structure for disks. Let's talk about how disks, which are secondary storage, compare to primary storage. So you can think of our primary storage as being our main memory, RAM, and our CPU cache, and our secondary storage as being a disk such as a hard drive. So the storage capacity for primary storage is much smaller than secondary storage, and the data persistence is transient, meaning it's erased after the process terminates, but secondary storage, the data is persistent. So data access speeds for primary storage is much faster than in secondary storage. So when we read data in from a database stored on disk in a secondary storage, we really want to be conscientious of how we're storing our data so that when we are going to access the data, it is as fast as can be because of how slow it is to access secondary storage. So let's take a look at if we chose to use a balanced binary search tree, such as an AVL tree, to store information from a large database like Google that has 33 trillion items. The estimated access time, if we used an AVL tree, would be big O of log base 2 of 33 trillion, which would be about 45 disk accesses. If we assume 120 disk accesses per second, then each search takes approximately 0.37 seconds. Let's also take into account that one disk access is about 10 to the 6 CPU instructions. What happens if you need to do a million searches? Very slow, very, very slow. What we really need to do in order to help speed up searches in large trees is to reduce the height of a tree. Binary search trees and AVL trees at best have heights log base 2 of n. If n is 10 to the 6, then log base 2 of 10 to the 6 is about 20. 20 disk seeks for each level would be too much. So we need to reduce the height of a tree by increasing the log base beyond 2. For example, if instead of a binary tree, we had a 5-array tree, meaning our nodes were able to have up to 5 children, then log base 5 of 10 to the 6 is less than 9, which is a much greater improvement over 20. So in general, instead of using binary, which are 2-array trees, we will use m-array trees such that m is greater than 2. So let's take a look at an example. Here I have a 3-way search tree. So we have nodes that have 2 data items and up to 3 child references. So as another example, 3 levels in a 3-way tree can accommodate up to 26 elements, and 3 levels in a 4-way tree can accommodate up to 63 elements. So shallower trees, but greater data items stored per level of our tree. So now we're ready to talk about BTrees formally. In a general BTree, we use an M-way or an M-array search tree, such that the tree height is log base m of n, where n is the number of nodes in the tree. Each node access brings in m-1 keys and m child references. Ideally, we want to choose m so that the node size is equivalent to 1 disk block size. So suppose this is 1 disk block, and here is our tree node structure. So we have m children, 0 base, so child 0 up to child m-1, stored in between keys that are going to separate our children based on our ordering. So the actual data stored is on disk at leaf levels of the BTree. So we're only going to store our actual data in our leaf nodes, and only keys are stored in the main tree. And the tree itself need not fit in RAM. When designing our BTrees, we should be aware of the following factors: that each one of our nodes should fit in 1 disk block, and we can help determine the parameters of our tree by asking questions such as, how big are the keys? What is the capacity of a single disk block? And then we can figure out what m is to figure out our tree height, which is going to dictate the number of disk reads, which is what we care about the most, because this is going to dominate our overall search time, is how many disk reads do we need in order to load the specified data into memory. So let's take a look at an example. A standard disk block size is 8,192 bytes. Let's assume keys. So keys are going to be our items in our internal nodes. Use 32 bytes, and child references use 4 bytes. So a child reference would be example child 0, child 1, child 2, and here are our keys. So 4 bytes for our child references and 32 bytes for our keys. This means the required space per node is 32 times m minus 1, because we have m minus 1 keys per node, plus 4 times m, because we have m number of children, and each child reference takes 4 bytes. We want to set this equal to 8,192 and solve for m to figure out that we can construct our trees for these requirements to be 228 way. That is, each node can have up to 228 children and 227 keys. So log base 228 of our original example, 33 trillion data items for the Google database equates to about 5.7 disk accesses. So each search in this tree, a 228-way tree, would take 0.047 seconds, which is a drastic improvement over our previous example, which was 0.37 seconds. So now let's talk about B plus trees. A B plus tree is a more specific version of a B tree. A B plus tree of order m is an m-way tree with all of the following properties. And we're going to define new parameters here, n, m, and l. So let's start with number 1. Leaves store the real data items. The root and internal nodes will store our keys. Number 2, internal nodes store up to m minus 1 keys, such that key sub I is the smallest key in subtree I plus 1. The root can have between 2 to m children. Each internal node except the root has between the ceiling of m over 2 to m children. All leaves are at the same depth, and each leaf node has between ceil of l over 2 and l data items for some l. And we'll talk about how to compute l. So for example, here is a B plus tree of order 5. So here's our root node, here's one level of internal nodes, and here are our leaves. And the leaves are where we actually store our data items. So in this example, m is set to 5. That's the order or the way of the tree, up to 5 nodes per children. And l is set to 5. And l is our parameter representing the number of data items upper bound for the leaves. And based on our restrictions here, number 4, each internal node except the root has between ceil of m over 2 to m children. Then each internal node has to have at least 3 children. That's the ceil of 5 over 2. And our last restriction here, each leaf has between ceil of l over 2 and l data items for some l. Well, in this case, l is set to 5, so each leaf node has to have at least 3 data items. So between 3 and 5 data items inclusive. So all of our internal nodes in our root node represent the index to the data. These nodes store only keys, and each internal node is going to be the same size as one disk block. Data items are stored at the leaf, so each leaf equals one disk block. Now let's talk about designing a B plus tree, and we'll work through a few examples. So how are you going to determine the number of children per node? And how are we going to determine the number of data items per leaf node, our parameters m and l? For the root and internal nodes, there are m child references. So if each child reference requires 4 bytes, then this is 4 times m bytes. And there are m minus 1 key entries. And since there are m minus 1 key entries, let's assume k is the number of bytes per key. So in a previous example, k was 32. Now we're going to generalize this. For leaf nodes, there are at most L number of data items per leaf, which means the storage needed per leaf is L times D, where D denotes the size of each data item. And we're going to specify that the size of a key should be less than or equal to the size of a data item. So values for M and L are chosen based on a disk block size B, a data element size D, and a key size K. So the root node in each internal node needs lowercase m equals 4 times m, so 4 bytes per child reference, m child references, k bytes per key, m minus 1 keys per node, total number of bytes. each internal node has to fit inside a disk block, implying that we let B, our disk block size, be equal to 4 times m plus m minus 1 times k. Solving the above yields that our lowercase m, which is the number of bytes for each one of our internal nodes, is set to the floor of b plus k over 4 plus k. So in an example, if k, our key size, is set to 4 kilobytes, and b, our block size, is set to 8 kilobytes, then m is equal to 1024 bytes, and that is the threshold for internal node capacity. For leaf nodes, L, which is going to be our maximum number of data items per leaf, is going to be the floor of B, our block size, over D, our data element size. So continuing with our example for a block size of 8 kilobytes, if D is 4 kilobytes, then L is 2048 bytes, is the threshold for leaf, not bytes, data items, is the threshold for leaf capacity. So that is each leaf can store a maximum of 248 data items, and the minimum, based on our restriction from our BTree definition, number 6, is going to be L over 2, the ceiling. So that would be 2048 over 2, which is 1024 data items. And lastly, we can figure out how many leaves are in the BTree by letting n be the total number of data items. There are between CL of n over L and CL of 2n over L leaves in the tree. So the next 3 examples are going to walk through common BTree operations: find, insert, and remove. So let's take a look at find. Suppose we have this 5-way BTree here, and we want to find 81. Then we're going to have to perform log base m, so 5, number of leaves, disk block, reads, and we can figure out how many leaves are in a BTree from our description above. So this is going to tell us how many disk block reads we need to do. Now, searching within each internal node would be log base 2 of m, assuming binary search. So once we're at a root or an internal node, we need to search through each of the data items in order to find which child reference to follow. So once we find which child reference to follow, and we continue doing this until we reach a leaf node, then we need to search within the leaf node big O of L, the number of data items. This would be a linear search to find the item. Or even better, if we are going to keep these in sorted order, which is the case for this example, then it would be log base 2 of L, because we could use binary search in order to search between 1024 and 2048, for example, data items. So in this example, we're looking for 81. 81 is between 66 and 87. Follow to this internal node. 81 is between 78 and 83. Follow through to this leaf node, and we see 81 is the last item in our list. Now let's take a look at insert. Insertion into a BTree ends up maintaining all leaves at the same level before and after insertion. This could mean increasing the height of the tree. So for example, let's insert 57 into the following BTree. So 57 is between 41 and 66. Follow to this internal node. 57 is greater than 54. Follow through to this leaf node, and there are only 4 items in this leaf node. We can have a maximum of 5. So we'll insert in sorted order because there is space in this leaf node. So here's what our tree looks like after inserting 57. So now suppose we want to insert 55. Following the same logic as before, we would insert 55 here, but we cannot because that would be 6 data items in our leaf node, whereas we can only have a maximum of 5, capital L set to 5. So we see that in the parent node, this internal node here, there is room to split the previous leaf into 2 parts. So we're going to split this leaf into 2 parts and add 57 as our new internal node key. And now we have 55 in our left child of 57 and our 57, 58, 59 in our right child of 57. Now, next, suppose we need to insert 40. So we're going to follow the same logic. 40 is less than 41. 40 is greater than 35. So it should go right here, but like in the previous example, this would be a violation. This would be 6 data items, whereas we can only have 5. So right now there are no empty neighbors, so we can't do the same approach that we did for inserting 55, where we split the leaf. So what we're going to do is instead, we're going to split our root node by shifting over. And now our root node is full, and we have room to insert 40 into a new internal node storing keys 35 and 38. And our original node over here, 8 and 18, now has 2 empty spots in order to grow its number of data items. An example for BTree delete or remove. Suppose we want to delete 99 from the following BTree. So let's find 99. 99 is greater than 87. 99 is greater than 97. So 99 is right here. So we could simply remove 99, but then our leaf node would only have 2 items in it, and we know that ceiling of L over 2 when L is 5 gives us 3. So the minimum number of data items that we have to have in a leaf node is 3. So if we were to move 99, we would have a violation of too few data items here. So instead what we're going to do is we're going to borrow a leaf from the left neighbor, and we're actually going to merge 97 and 98 into the neighboring leaf node, which will make it full now, but we do have room here to split as needed.